Hey y'all, my name is Hammaad, and today we're going to be talking about atoms, atoms and atomic weight, okay? So, first let's talk about atoms. You see my hand, you see the table, you see the board, everything is made up of very small substances called atoms, okay? Atoms are the basic building blocks of all things that contain mass. That's probably not the right definition, but everything you see around is, if you go down to it, the smallest thing that make up everything are called atoms, okay? So atoms are made up of three different parts themselves. That kind of sound weird because I said that was the smallest thing, but atoms in itself, those are the smallest thing that make everything around us, but they're made up of three different parts, okay? They're made up of protons, neutrons, and electrons, okay? So here's what an atom typically looks like. Right now I'm going to be drawing an atom. So it has one proton in the middle. This one only has one proton. One neutron, and then one electron. This going around and around this area called the nucleus. The nucleus is condensed region where all the protons and neutrons stuck together. So a proton has a positive charge, an electron has a negative charge, and a neutron has no charge, okay? So the protons and neutrons are collected in the middle, while the electrons, they're just going around and around outside of the nucleus. They're going around the nucleus, okay? So now that we know what an atom looks like, and we know what an atom is, let's look at the periodic table a little bit to go into that a little bit further. So right now I'm writing this right here. So what is that? So if you go to the periodic table and you go look to the right a little bit, you see this right here. What does that mean, Hammaad? Well, I'll tell you. I'll show y'all. So this right here, this number on top of the letter C, that is the number of protons. So this whole thing right here, first off, this is one of the elements on the periodic table. An element is the pure substance where the atoms or atom contain the same number of protons. And that's where this comes in handy. So the number of protons defines what element an atom is. So let's say I had, this element is called carbon. So let's say I had an atom with 2 protons. That would be helium. I'll get to the bottom number in a sec. That would be helium. If I had an atom with, let's say, let's think, 8 protons, okay? That would be the element for that atom would be oxygen, okay? So the number of protons define which element we are talking about when we're looking at an atom. Okay? And lastly, we have this number, which is the atomic weight. And I will get right into that right now. Hey y'all, it's Hammaad. So today we're going to be talking about atomic weight and atomic mass, okay? I know I'd continue in the last video, but I got kind of lazy, so let's get this stuff. So if we're talking about atoms and anything we really look at, we really attribute a lot of things masses, okay? So my hand probably weighs, this is probably way off, but 100 grams, okay? Or this probably weighs 2 grams. I'm way off. I don't know, it probably weighs like 40 grams. But anyways, if we look at things, we usually give things masses, okay? But when we're talking about atoms, those are very small and very light because of how small and how minuscule they are, okay? And the basic building block of anything we do. So the way we measure the mass of atoms, we use units called AMUs, or known as atomic mass units. Okay, so AMUs are atomic mass units. Okay, and every different types of atoms have different atomic masses. Okay, that's how you refer to the atomic masses. So, for example, let's say we're talking about an atom of carbon 12, and we'll get to why that's called 12 in a little bit. But carbon 12, we know that carbon has 6 protons because that's the only atoms with 6 protons are known for the element of carbon. That can't change. Okay, so carbon has P 1 2 3 4 5 6 1 2 3 4 5 6. Okay, let's say this is the equibalanced carbon atom with equally balanced, and like the charges are equal. So 6 protons, 6 neutrons, and then 6 electrons. Okay, the atomic mass for this carbon atom would be 12 AMUs. Okay, and the way we got this was we added the number of protons plus the number of neutrons. So this carbon 12 atom has the atomic mass is 12 AMUs, and the way we got that was we had 6 protons plus 6 neutrons, which equals 12, and the reason why I said that, because when you usually look at atoms, we say that 1 proton is about equal to 1 AMU, and then 1 neutron is about equal to 1 AMU. And then we say, what about the electrons? Well, that's why this is kind of equal, because when you have electrons, we say that they have a negligible mass, which means it's not really contributing enough to be noticeable. It contributes just enough for these two to equal out to 12. So that's how we got that its atomic mass was 12. Okay, now in the last video we saw 12.01. Well, if we look at this, I called this the atomic weight. That's different from the atomic mass, okay? Because first off, we can see that it says 12.01. Well, you can't. When we just looked at the carbon 12 atom, it had 12 AMUs worth of mass, and its mass was 12 atomic mass units. So why does, when you look at the periodic table, say 12.01? Well, that's the atomic weight, and this is how it works. So atoms can have the same number of protons. Different atoms, okay, so atoms with the same number of protons can have different number of neutrons. And that's where we get the term isotope. Isotope is when the atoms have the same number of protons, but different number of neutrons. So an isotope is when atoms that have the same number of protons have different number of neutrons. So here's where it comes into play. For example, let's say you have, I'm not writing the whole thing. Let's say you have carbon 12 and then carbon 14. They're both carbon because we know that they have 6 protons. 6 protons. However, this carbon atom has 6 neutrons. And this has 8 neutrons. And this number right here was referring to the atomic mass of each individual atom, okay? This one has an atomic mass of 12, atomic mass of 14, and this is not the abbreviation for atomic mass. I just made that up right now. But we see how these two are isotopes of carbon, okay? One has 8 neutrons, one has 6 neutrons, but they both have the same number of protons, making them both carbon, okay? And that's where we go into the atomic weight. So there are isotopes of elements out there in the world. However, one isotope may be a lot more abundant than the other. So where we had carbon 12.01, there might be a bunch of carbon 12s in the world, like a lot of them. And then there might be a few carbon 13s. So when we take into account the abundance of each one of those, and then you add them, abundance plus times the mass, and you add them together, you see that the averaged out weight of all the masses of the isotopes comes out to that. So what this would look like would be, let's say, I had this specifically in my notebook, but can't really access it right now. I left it somewhere. But let's say this was 98% abundant on Earth. Okay, carbon 12, the carbon 12 isotope. And the carbon 13 isotope was 2% abundant. So the way we would get the abundance right here, the atomic weight right here, we'd take 12, which is the atomic mass, times the 0.98, which was the abundance. And this is all carbon 12. Then we add that to, 13, which is the atomic mass of this atom, times the abundance that we know of. Okay, and the way you find the abundance, I'll explain that in a later video. So once you add these two together, although this doesn't equal exact that, and I know these abundances are wrong, let's just say that the calculations were correct, it would come out to 12.01, which would give us the atomic weight, So thinking about atomic weight and atomic mass is specific to an individual atom. So a carbon 12 atom will have an atomic mass of 12. No, an atomic mass of 12, yeah. And the atomic mass of carbon 13 will have 13 AMU. And the carbon 12 would have 12 AMU. But atomic weight is like the average of all the masses and their abundance, and taking all that into account, the average mass of all the different isotopes of that specific element taken into one. So I don't know, average of all isotopes taking abundance into account and everything. So good job, y'all. Thank you.